Hi everyone. Today's topic is type inference and parametric polymorphism. The first part of today's lecture is gonna talk about type inference. We're gonna continue the lecture we learned last time about type inference. We're gonna implement that type inference part. And the second part and the third part of today's lecture are gonna talk about parametric polymorphism. Parametric polymorphism is really important, and we are going to learn parametric polymorphism in this lecture and subtype polymorphism in the next lecture. As we learned last Wednesday, type inference is to infer types from programs, meaning that in an expression, we may have some identifiers, x, y, ABC, like that. And in explicitly annotated types, when they are introduced, like function parameters or identifier introduction, they may be introduced with their types. That's called explicitly annotated types. Because programmers are lazy, and many programming languages do not require all the types to be explicitly annotated, but they are trying to infer types for programmers so that programmers can use the language more easily without the labor of writing down types by themselves. So there's type inference, inferring types. And in order to infer types, we need to know where to infer, where to put the types. So in this language, in this simple language, we require that omitted place annotate with this question mark in concrete syntax, right? And in the implementation, we just make an option of type. Option, that's either none or some, either of those. So in the beginning, when we have question mark, we give it type variable t. So that's why we call this var t. A type is either number type or arrow type or type variable, which are used to set up type equations of type variables and some other types, so that we can infer what that type variable is. So in the beginning, we don't have any hint, any idea about this type variable. So it's going to be none. And later, when we compare some types with this type variable, and we know that that should be Boolean or number like that, or arrow type, then we have that hint, and it's going to be written here. That's why it's option type. Type unification, it's trying to make two types the same. So type unification is an algorithm which takes two types, tau1 and tau2. So for given two types, tau1 and tau2, it first resolves them. Resolve meaning simplify them. We're going to see the definition of the resolve function again later. So when we simplify those two types, tau1 and tau2, let's call those simplified resolved types tau1 and tau2 again. And there are three possibilities because tau is either number or arrow or what? Type variable, right? So tau, when we compare tau1 and tau2, when we try to unify tau1 and tau2, the first case is when tau1 is a type variable. Tau1 is a type variable t, or tau2 is a type variable, or none of them is type variable. That's three cases. And when tau1 is a type variable, what was the algorithm that we learned last Wednesday? If tau2 is already the same with t, then they are already unified, so succeed. If tau1 occurs in tau2, then we are in trouble because we cannot solve this recursive equation for type variables here in this simple language. So we are going to fail it. Fail meaning tau1 and tau2 cannot be unifiable. Tau1 and tau2 cannot be the same. Otherwise, we put that information that this tau1 t should be unifiable with tau2. Set up that equation and put that information into t and succeed. Right? How did we implement that? This unify function takes two types, t1 and t2, and then let's resolve that. Simplify them. And when the first one is a type variable, that's the first case. The other two cases are this ... When tau1 is a type variable, then let's check. There were three sub-cases. The first case, when tau1 and tau2 are already the same, we are done, succeed. When tau1 occurs in tau2, we are in trouble because it's a cycle. The cycle cannot be solved in this language, so cyclic type, error. The third case is, oh really? Then tau1 should be the same with tau2. Let's remember that in tau1. Tau1 is a type variable, so it has this field option of some type. In the beginning, it was none, and now that we know tau1 should be the same with tau2, put that information. Tau1 is unifiable with tau2. The second case, when tau2 is a type variable t, then swap tau1 and tau2 and the same as the above, right? So actually we can do just the same thing, just the other way around, meaning, yeah, the second argument is a type variable. If they are already the same, we are done. If tau2 occurs in tau1, that's a cycle. Otherwise, remember that tau2 should be unifiable with tau1. But how many lines? Ooh, it's really bad to have copy and pasted code because it's error prone. Okay, and when you need to fix some error, some bug in the previous code, it's highly likely that we forget to fix this one again, right? So we'd better reduce the code duplication. That's one of the important principles in good programming. So instead of having these repeated code, we'd better have unify T2, T1 and reuse the code before. Okay, the final case, if none of them, tau1 and tau2, both are not type variables. If both are none, we are done. If tau1 is an arrow type, tau2 is another arrow type, then we need to check those parameter types, unify tau3 with tau5, and then return type, unify tau4 with tau6. Otherwise, meaning num and arrow type and arrow type and num and arrow type, but their parameter types or return types are not unifiable, fail. That was the final case. How do we implement that? Yeah, the final case is num, good. Arrow, check the parameter types, check the return types. All the other cases, errors. Those cases that I mentioned, like arrow type, but their parameter types or return types are not unifiable, that had to be signaled by this or that. If those parameter types are not unifiable, error is going to happen here. If return types are not unifiable, error will be thrown here. Okay, so two extra helper functions. Remember, resolve, simplify a given type. What do we mean by simplifying a type? What do we need to resolve? Because again, type is either num t, arrow t, or var t. And var t has option type. So that option type may have var t again. So it could be nested like an onion. 양파처럼 까도 또 나올 수 있죠? So we are going to get rid of those extra unnecessary wrappers, saying that resolve, take a type. If it's not a variable type variable, then just return it. If it does not have any type information nested, return it as it is. If it has some type information, resolve that type information. Okay, occurs because this type language is simple. We are gonna reject this kind of equation like T1 equals T1 arrow T2 like that. Oh, we are solving this problem? No, we cannot in this simple language. So we are gonna check whether a given type variable occurs in a given type. If the type is numpty, it's not possible to contain type variable, so false. If a given type is an arrow type, then we can check whether the parameter type contain this type variable or the return type contains the type variable. If a given thing is type variable, then if they're the same, that occurs. Otherwise, it does not occur. Okay, so unify, there have been several frequently asked questions about this unify function, which was what? The unify algorithm doesn't seem to right. It looks like some cases are missing. Yeah, if you think so, draw some table with what? numt, arrow t, and type variable. numt, arrow t, and type variable, and see whether we covered every case. Then you can see the correctness of the algorithm. What if the type of the whole program is a type variable? Oh, really? That's interesting. When would that happen? You think about it. When would the entire program have a type variable? When we type check that. That's when we don't know what its type is, like throw. It could be alpha. Okay, think about it. What does the occurs function mean? I just explained that, and I'm gonna just leave it for you to memorize that or remember that again. Now, this is the language for implementing the type system, the type checking algorithm. We have the usual arithmetic expressions, lambda calculus, if zero, and function definition, recursive function definitions, right? And then num type, arrow type, and question mark. Let's try to implement the type checker. Type check. What's the type of a number expression? numt. So when an expression is a number expression, its type is numt. Simple. What about addition? Addition? Let's look at this typing rule. Again, you're gonna have project number 3 today, and it's pretty big language, so you'd better start early. And it has a concrete syntax, abstract syntax of the language, and then it has type system and dynamic semantics, operation semantics. And we do have really detailed description of the operation semantics and type system, and those long description in English is also accompanied by appendix A and B with these rules. So you may find one way more natural to you than the other, but we provide both of them. So I hope you read it earlier than later. Let me repeat this in Korean, and then I'm going to talk about project 3 at the end of today's lecture. 프로젝트 3 이따가 수업 마지막 시간에 얘기하긴 할 텐데 언어가 조금 커요. 마지막 프로젝트니까. 그래서 concrete syntax, abstract syntax, type system, dynamic semantics 다 영어로 꼼꼼하게 이게 무슨 뜻인지 썼고 appendix A, B에 이런 식으로 룰로 썼어요. 그래서 두 개가 다 똑같은데 어떤 사람한테는 영어로 쓴 게 더 이해하기 쉽고 어떤 사람한테는 수학으로 쓴 게 더 이해하기 쉬울 수 있는데 매우 길기 때문에 그리고 생각보다 크기 때문에 가능한 일찍 시작하세요. 나중에 시간 없어서 쫓기면 못할 가능성이 적지 않아요. 일찍 시작하세요. So yeah, this rule reminds me of that project 03 because it's pretty long document. Okay, under some type environment gamma, E1 plus E2, what's the type? In order to know the type of E1 plus E2, we need to know the type of E1 and make sure that has num type. We also require that the second sub-expression also have type num. Then addition has type num. That's the rule, right? You should be able to read these rules to do project number 3 and to be prepared for final exam. Type check. It takes an expression and a type environment and produces a type, right? Under a given type environment, what's the type of this expression? That's tau. Type check. An expression with type environment is going to be some type. Otherwise, type error. So addition of L and R, how do we type check that? Oh, look at that, unify. That's why we implemented unify. We are saying that the type of the first sub-expression should be numt. The type of first sub-expression should be numt. The type of the second sub-expression should be numt. The type of the second sub-expression should be numt. Should be numt, unify. Unify meaning the type of this expression should be unifiable with numt. Remember? Yeah? If the type of this was numt, then numt, we are done. If the type of this all is arrow t and numt, error. If the type of this all is type variable t, ooh, really? Does it have any information like some tau, or is it none? If it's none, oh good. Hey you should be numt. How about some tau? Then we need to unify this tau and numt like that. Okay. Type check an identifier. Then this identifier should be defined in this gamma. X should be in this domain of gamma. Then, oh yeah, let's get the defined type in gamma. ID, okay, look up the type environment and get the type. If the name is not in the environment, throw an error. Free identifier error. I don't know what it is. Function expression. Oh, yeah, look at that. Function expression now has the type annotation of parameter. Then what? We need to check the welfromness of tau1 because it's written by a programmer. And then check the type of the body under extended type environment. Extend this given type environment with this parameters type information. Check the body and get the type. And the type of the function expression is going to be this arrow type. What's the type of function expression? Check the validity of the annotated type, and the result is going to be arrow type with the annotated parameter type and the type of the body expression. The type check the body using this type environment. So far so good? Yeah, nothing surprising. How about function application? Function application. Let's see. What can we do? Yeah, remember we can check like E1, E2. We need to check each sub-expression. The type of the first sub-expression should be some arrow type, and the type of the second expression should be the type of the parameter type. Then the type of the function call is going to be the return type. How can you check that? There could be several ways to implement this type checking. First case is what? Just check everything piecemeal, meaning that check the type of the first sub-expression, call it fun-t. Check the type of the second sub-expression, call it arg-t. And then, hey you, fun-t, you should be an arrow type. Otherwise, error. If it's an arrow type, then it should have a parameter type and return type. If the type of this parameter type of this arrow type is just the same with argument type, then we are good. Return the result type. Otherwise, an error. Yeah, it's very descriptive. It explains what we do in this rule, right? Very clearly. But we can simplify this implementation like this. Just the same, but by taking advantage of unify. Very simple, right? What is that? The type of function call, FA, the type of that is some type variable. Let's infer the type of this function call. Really? What's that? What do we know? What we know is that the type of the first sub expression, the type of first sub expression should be an arrow type. That's what we know. And arrow type from what? The type of the second sub expression. The type of the second sub expression. And then what's the result type? We don't know. Let's infer that. That's the trick. Isn't it cool? Yeah? That's the secret that we can take advantage of this unify. Do you see what's happening? One more time. Let's say the type of function call. What is the type? Remember when we discussed this type inference last week? We said that when we don't know the type, like the question mark annotated to a function parameter, give it type variable, t1, t2, like that. And another place to introduce type variable. Remember? When was that? Function call. If you don't remember, go back to the slides. So for function call, we introduce a type variable and try to get some hints out of those sub-expressions. How? Yeah, just set up an equation. Hey, the type of the first sub-expression, that that should be an arrow type from the type of the second sub-expression and the result type. Then in this unify function, we are going to type check this function part, and we may have some type of that. If it does numt, error. That unify will throw an error. If it's an arrow t, wow, then it's gonna have some parameter type and return type, and this unify function will check whether the parameter type and this argument expressions type is unifiable. And that unify is also check whether the type of this result is what? Unifiable with this type variable, meaning this information is gonna be stored here. Woohoo! Mutate, right? And then after unify, we got that information here, so return it. Cool, right? And the other two expressions are simple as usual. If 0, the first sub-expression should be num type. The first expression's type should be num type. The second expression and the third expression, they should have the same type. Which one, I don't care, but that's going to be the result type. So type check the second sub-expression true branch, and that should be the same with the last sub-expression first branch, and the type of the whole expression is going to be that type. Finally, recursive function, when we have recursive function xf, whose parameter x has type tau1, and the result should be tau2, and the function body expression and the use side of that function. Then there's only one type annotation tau1 that should be well formed. And there are two. So the parameter type and return type both are annotated, so they should be well formed. And we are gonna check the type of this body expression because it's a recursive function definition. In the body, we may have the function name and parameter name. So put those two pieces of information into the type environment, type check that. That should be what? The return type. Then finally, type check this expression. This time we are not supposed to add x because that's not available, but extend gamma with only the function name. And type check it, that's going to be the type. So recursive function f which has parameter x, whose type is xt. The type of result of this function call is going to be lt, a body expression, and an expression to use. So check the validity of parameter type and return type, and make an arrow type for this function xt to lt, right? And extend the type environment to have this functions type. That's going to be the type environment to use this expression. But before that, we need to unify the return type with the type of the body expression. When we check the body expression, we need to use the type environment, the given type environment, and the functions type and the parameters type. Now let's take the first break and come back for the second part of today's lecture.